In the last class, we discussed about the concept of linear programming and when a problem can be solved using linear programming. Today, we are going to look at actual formulation of the linear programming model. For this, I have taken up an example. If you look at this example, here it says a company has two grades of inspectors, 1 and 2, to undertake quality control inspection. That means these two grades of inspectors, they are taking up the job of inspecting the material manufactured by this company. At least 1500 pieces must be inspected in an 8 hours day. Here there are certain points you must keep in mind. At least, look at this word, at least 1500 pieces must be inspected in an 8 hours day. These are the points we are going to keep in mind. Grade 1 inspector checks 20 pieces in an hour. So, if it is the grade 1 inspector, he is capable of checking 20 pieces within an hour with an accuracy of 96%. Accuracy of 96% means what? That out of 100, the 96 results that he gives are correct. So that means 4% of 4 results he gives are not correct. Then we have grade 2 inspectors who check 14 pieces an hour. So grade 2 inspector is checking 14 pieces an hour with an accuracy of 92%. 92% accuracy means out of 100, 92 cases are there where this particular inspector is correct in his assessment. That means if he says the material is good, it is really good. And if he says the material must be rejected, it should actually be rejected. But there are 8% cases where he may pass a faulty item, or he may he may pass a faulty item, or he may accept something, or he may reject something that shouldn't have been rejected. That means it was good. So the daily wages of grade 1 inspectors are rupees 5 per hour. That is, if you are employing a grade 1 inspector, you are paying him rupees 5 per hour, and if you are recruiting a grade 2 inspector, you are paying him rupees 4 per hour. An inspection error costs rupees 3 to the company. That means if a faulty item is accepted or a good item is rejected, the company bears the brunt of rupees 3 per such acceptance or rejection. Now here is a constraint for you. There are 10 grade 1 inspectors. That means even if you want, you cannot utilize the services of more than 10 grade 1 inspectors. And there are 15 grade 2 inspectors. That is, even if you want, you cannot utilize the services of more than 15 grade 2 inspectors in the company. Now you will notice there is another constraint. At least 1500 pieces have to be inspected in a day. So this is a constraint for you, that is at least, and here it is at most. At most so many grade 1 that is at most 10 grade 1 inspectors are available, and at most 15 grade 2 inspectors are available for service, and at least 1500 pieces must be inspected per day, and in a day you have got a shift of 8 hours. Now comes your objective. Find the optimal assignment of inspectors. Optimal assignment of inspectors that minimize the daily inspection cost. Your objective, this is a minimization problem. You want to minimize the cost of inspection. Now, in this problem, what are the costs that we are bearing? We are bearing the cost of paying these inspectors at the rate of rupees 5 per hour and rupees 4 per hour, depending on whether they are grade 1 inspectors or grade 2 inspectors. If they make a mistake, we are bearing the cost of rupees 3 per inspection if there is a mistake. So these are the costs we are bearing as far as inspection is concerned. So let us find out how we can minimize the daily inspection cost. Now let us start off by creating our decision variables. So our objective over here is to find out how many grade 1 inspectors and how many grade 2 inspectors we should employ to minimize the cost of inspection. Now let us assume that x1 represents the number of grade 1 inspectors and x2 represents number of grade 2 inspectors. Okay. Now our objective, let us start off with our objective function. So if we look at our objective function, our job is to minimize the inspection cost. Now let us calculate the inspection cost. Now let us look at cost of a grade 1 inspector per hour. Now see, we are paying him rupees 5 per hour plus what is his probability of making mistakes? It is 4%, that is 0.04, that is out of 104. So I divide 4% by 100 and 4 by 100 and I get 0.04. So now he is making 0.04 error out of 20 because in an hour he is capable of inspecting 20 pieces. That is given in the question. That means out of 100 he makes 4 errors. So how many errors will he make out of 20? It is 0.04 into 20. And the cost of such error is rupees 3. So that means this is the total cost borne per hour for a grade 1 inspector. Rupees 5, which I am directly paying to him. The number of mistakes he is making is 0.04 out of 20, 4 out of 100. So 0.04 out of 20, and that when multiplied by the cost per mistake 3, we get the total cost we are bearing for one grade 1 inspector, which comes to rupees 7.40. Now similarly, if we calculate the cost of a grade 2 inspector, so let it be cost of a grade 2 inspector per hour, it is coming out to rupees 4, the amount we pay him per hour, plus he makes 8% mistakes. So that means 0.08 multiplied by he inspects 14 items per hour given in the problem. So this multiplied by 3, the cost of an error. This entire thing is the cost we bear for one grade 2 inspector, which comes out to rupees 7.36. Now if we add up these two costs, now see how do we go about. Now if in an hour this man makes that is the cost of a grade 1 inspector per hour is 7.40, then in a day we have a 8 hours shift. So the cost comes out to, so daily expenditure, daily cost comes out to be 7.40 into 8, which is equal to 59.20. 59.20. So it comes out to 59.20. Similarly, for a grade 2 inspector, the hourly cost is rupees 7.36. In a day, we have 8 hours, a shift of 8 hours. So your daily cost comes out to be rupees 7.36 multiplied by 8, which gives us rupees 58.88. So if I try to find the objective function is to minimize the daily cost of inspection. What is the daily cost of inspection? The daily cost of total daily cost of inspection is cost on grade 1 inspector per day plus cost on grade 2 inspector per day. So for grade 1 inspector, it is 59.20 per grade 1 inspector. So if we are having x1 number of grade 1 inspectors, so the cost is 59.20 into x1, plus for every grade 2 inspector our cost is 58.88, but we are having x2 number of grade 2 inspectors, so the cost becomes 58.88 x2. Why did we say that? Because right in the beginning we have assumed that we are having x1 number of grade 1 inspectors and x2 number of grade 2 inspectors. So this has to be minimized. So we will say minimize z equal to 59.20 x1 plus 58.88 x2. So this becomes my objective functions. Now, which are my constraints? My first constraint is, so this is said to be subject to. Now the constraints are written like this: subject to minimize z equal to 59.20 x1 plus 58.88 x8 58.88 x2, subject to x1 less than equal to 10, because you have only a maximum of 10 grade 1 inspectors, x2 less than equal to 15, because you have only 15 grade 2 inspectors. And thirdly, you see x1 is, now you have got in a total day, you have been told that 1500 units have to be checked per day. Now what do we find? In 1 hour a grade 1 inspector checks 20 units. So 20 units. Now every grade 1 inspector in an hour checks 20. In an 8 hours shift checks 20 into 8, and there are such x1 number of inspectors whom we are employing. So one grade 1 inspector checks 20 pieces per hour. In a day of 8 hours he checks 20 into 8. So if there are x1 number of grade 1 inspectors, the grade 1 inspectors check 20 into 8 x1 number of pieces. Similarly, one grade 2 inspector checks 14 pieces in an hour. This multiplied by 8 hours shift, for one inspector he checks 14 into 8 in an 8 hours shift day, and we have x2 number of such inspectors. So this total quantity checked has to be at least 1500 per day, or if we simplify it, it comes out to be 160 x1 plus 112 x2, which has to be greater than equal to 1500. So this is my objective function. this is my grade 1 inspector constraint. This is my grade 2 inspector constraint. And finally, this is my number of pieces inspected constraint. So this is the formulation of the LP problem that we are currently looking at. So remember that if you are asked to formulate the problem, you don't have to solve it. You just have to show the model. This is one minimization problem that I have discussed in this video. In the next video, I'll be discussing a maximization problem, and after that we will move into solutions of linear programming problems. So this problem boils down to minimize z equal to 59.20x1 plus 58.88x2 subject to x1 less than equal to 10, x2 less than equal to 15, 160 x1 plus 112 x2 greater than equal to 1500. And there is something we have missed out, the non-negativity restrictions, that is x1 greater than equal to 0, x2 greater than equal to 0. These are called the non-negativity restrictions. That means all your decision variables, all your linear programming variables must not take up negative values. So at this point, I will like to give you another clue before I end this video, that is, in case of a maximization problem, your constraints are usually less than equal to constraints, because if you are trying to maximize your objective, the constraints try to pull them down. So they are saying this resource is less than this resource is less than this. If it's a minimization problem, so where you are trying to minimize, let us say, the cost, in that case your constraints pull you up. They are the greater than equal to constraints. That means at least so many units of the item must be inspected in a day. At least so much must be produced in a day. At least so much must be sold in a day. So these constraints are greater than equal to constraints. So when you are trying to reduce cost, they try to pull your cost in the opposite direction. That is why a linear programming problem exists, where we try to find the best possible solution. So with this, we'll end today's class. In the next class, we will discuss the model building of a maximization problem.